I'm just testing the mic with Andy. He's recording. Good? Perfect, perfect. Looks like this mic is only for the recording, but yeah, I'll just have to speak loud here. I guess this is okay. It's perfect. So yeah, I can do that. I can do that. Yeah, it's probably up to Andy. It's about time. All right. Thank you guys for coming on a Good Friday to this seminar. My name is Joe Yan, and some of you have seen me before on campus. I'm a professor in civil engineering. Have been working in this college for 15 years now. So I'm one of the old guys on the faculty. And my expertise is in geotechnical engineering by training. So I work on soils, frozen soils, permafrost, frozen soil, structure interaction, design of bridge foundations, considering the impact from the frozen ground during seismic events. That's some of the research projects I have conducted for the DOT and some funding agencies. I'm not going to be talking about earthquakes today, okay? But I'm here to share I think it's a very exciting research to try to come up with an alternative for insulation. You guys are familiar with insulation, construction in the Arctic or in the cold regions here. Growing insulation from fungus and forestry byproduct or agricultural waste. We don't have much of agriculture here, but we have plenty in the lower 48. So lots of waste that's being dumped, disposed one way or another. So can we make use of those to make materials that's useful for our infrastructure construction or not? Okay, so talk about the motivation and objectives of this research, and talk about the engineering process. It's bioengineering, since we are working with fungus. And of course, I'm going to talk about the engineering properties of this material we came up, and talk about large-scale production. Many of you would be curious, and some future work, some challenges we're facing, we want to overcome before eventually we want to put in the market here. That's the ambitious goal. Okay, commercialization. But at the end, I'll summarize this research. Talk about motivation. You guys probably have seen plenty of plastics, polymers, petroleum-based products being used and being dumped everywhere. Lots of stuff. Expanded polystyrofoam, used for packaging, insulation. We use a lot of them here. Examples, fishing, those bulbs or boils. You just have lots of waste being disposed. And back to Alaska, any construction project in Alaska, you have to use some sort of insulation material, either it's been fiberglass or polystyrofoam. Here's the parking lot right in front of this building. During last fall, am I right? Or last late summer, because of the differential, settlement, the frost heaving, we had to dig it out and put a layer of insulation here so we can limit the frost penetration to control the frost heave, particularly differential frost heave, so that the parking lot is still flat, at any time of the year. And last year, it was not the case, okay? And this is a segment of highway on the Dalton Highway approaching to Prudhoe Bay, probably already. It's on permafrost. Once you build a highway, you strip the vegetation, all those organic soils. That's almost like taking off our jacket. So the insulation that's already there in the nature for the permafrost is gone. Given time, the pavement is absorbing heat from the sun. It's melting the permafrost, causing the settlement or differential settlement, damage on pavement. So at some point, they just decided to rip it off, rebuild it, a layer of insulation, miles and miles of them, okay, used to make it more last a little longer. I would say that's the idea. So all those traditional insulation materials that we use, they are definitely, very light, hydrophobic. That means they are not attracting water, moisture. They are very inexpensive. Okay, you go to Home Depot, you buy a bunch of them. They're fairly cheap. However, because it's based on mineral or petroleum products, it's not sustainable. It's non-renewable. And most importantly, okay, this thing, it's plastic. You dump it in the environment, it's not going to break down in hundreds, if not thousands of years. It's going to be there for many, many, many generations, So every year we dump a lot of them. Okay, this is a French government estimation, 14 million tons of this very light material. So huge volume of material is dumped in landfill, running out of space quickly, especially for this big metropolitan area. I know for one thing in China, they are trying to find a place to bury the trash, too much. The land is very limited. You have to haul them a long way to bury them, And burning them is definitely not an option. Lots of toxic gas being disposed to the environment, to the atmosphere. And it's also detrimental to the wildlife. Fish, wild animals, they inhale it, they eat them, they die, basically. Now, back to the idea we're trying to explore, the bioengineering process. The specific process we try to use is the mushroom, fungus. Okay, we are, this is a basic, cartoon showing the structure of the fungus. You guys are familiar with mushrooms. Okay, the top portion is the edible, the fruits, the fruiting body that we eat. And the spores are produced by those myceliums. Those are called reproductive mycelium. The system supporting the fruiting body. And then at the bottom, the root, okay, that's the so-called, vegetative mycelium that is trying to find any nutrients that it can find, that trace, waste material, organics, to by to it's going to produce enzymes to digest it, so that it can reproduce. So all those myceliums, they are consisting of those hyphae, the filaments like our hair. Okay, that is the mycelium, fungal mycelium. That is the part, not the fruiting body, but the root system that we're trying to take advantage of to bind together with our material and form some sort of stuff. But more on the fungal mycelium, those are the filaments that is composed of long thread-like and connected end-to-end cells. Okay, in the cells, in the wall of the cells, it has a special naturally produced polymer. It's our plastic, but it's naturally produced polymer that it's some kind of a carbohydrate. It's like our fingernail, okay, or our hair, or the shells of the insect. It's very same material, but it's naturally produced. That actually add the rigidity and structure support to the cells, to the hyphae, to the filament that we are trying to take advantage of. Okay, so that is the key. That is the science of this project, of this idea. You go to the forest, you find any dead tree, you can see those white stuff. Those are the fungus, some kind of mushrooms growing there. Okay, the white stuff, if you zoom them in, look like this. This is about 2,000 times of amplification under a scanning electronic magnifier or microscope. That, those are almost like our hair, but randomly woven together that forms a matrix. So the idea of this project is to take advantage of those fungal mycelium and combine them with our substrate, feedstock, natural fibers, sawdust, agricultural waste, plus some additional nutrients, additives, and form a matrix. So it's a three-dimensional matrix that is bound together, by those myceliums of all those feedstocks, the stuff we add to form a form we call the bioform. And that material itself, because of the filament itself that we use, okay, because of the air that's trapped inside, the filament, it's hollow. So lots of air inside. Insulation is about how to fix the air, right, in your jacket, either it's feather or stuff or fabric. Tom, you have a question?
Yes. So is the fungus actually consuming the waste?
Yes, it's consuming a portion of that.
That was a trick question because I actually
it does.
Yeah. Asked you a question.
Tom Ravens has a question. Is the fungus consuming the substrate, the feedstock? Yes, 100% true. That's the point. For the fungus for the mushroom to grow, it needs nutrients. Okay, so the forest waste, sawdust, or agricultural waste provides majority of the nutrients. So it's trying to find moisture and nutrients to grow, to colonize. Yeah, it does consume a portion of that. And then you still have some residuals left over. And that's what we bind together to form a matrix. So majority is air, actually. So that's why the material is light, okay? It's attractive properties here. Here's a cartoon I like to demonstrate, to show the totally different two approaches, manufacturing versus bioengineering here. For our conventional insulation material, the expanded or extruded polystyrofoam that you use the petroleum product and you put it in the factory that's going to do the expansion. You have the energy input, you have emissions of the stuff, so it's manufactured very quick. Conventional insulation material, the blue boards you buy from Home Depot. Okay. Now for the bioengineered material, we're taking advantage of the mycelium. We promote the growth of this mycelium in a matrix in a controlled manner. The matrix is formed of mostly agricultural waste or forestry byproducts, plus some ingredients that we form this bioform or mushroom insulation nickname. So manufacturing versus growing, and it's very different. It has a totally distinct properties. Your impact or footprint. I'm going to talk about it later. But yes.
So where is it made? I mean, like that board that you showed, the mushroom insulation.
Right.
Where's it made? Like, is it made in a factory or?
Yeah.
Is it just...
I'm going to talk about that.
Oh.
Yes.
All right.
Yeah. One question was, where is the mushroom insulation material is made? It's not made yet. It's not available in the market. Okay. We are trying to make them. And I'm going to show you some preliminary results. We have 4x8, panels already produced, look pretty good. It's just a matter of how to mass produce them in a.
It might be like an industry building.
There could be, yeah. That's the goal. We want to produce this material and market it so that people can use that. Okay. So this study, we had a couple of phases, phase 1, phase 2. First of all, is to prove the concept. Is this doable? Can we do that? Is the material produced going to be useful or going to be comparable to the commercially available material, to the stuff you can buy from the Home Depot? Can we do that? Can we get there? Okay. How to optimize the process so that we can do it in a time, efficient. How long it's going to take. We don't want to take months or years to grow, right? It's going to be too slow. We want to do it very quickly, consistently. So I'm going to present some data to compare those key properties, like R value, for example. The density. The toughness. The modulus of elasticity, the flexural strengths, with the commercially available material. And then some prototype process for mass production. Okay, I'm going to show you some ideas over there. I'm only going to talk about some key aspects. The bioengineering process is pretty complex here. Many of you probably, don't care, but some key aspects about the process. First of all, you cannot just use a mushroom, right? Not just any mushroom to produce this material. It has to be a fairly unique mushroom that we selected actually is from Alaska that has a very tiny floating body, because that's not the part we don't want to use. It's kind of, weak and it's edible, right? We want the tough, the vegetative mycelium part, the root of the mycelium part, to use that. So it's a special type of mushroom that can survive in cold temperature, that we have found that is very promising. And then the second item would be the nutritive substrate, the feedstock. What do you use to grow the mushroom? Which one would be more effective? What is the percentage, of the combination? Okay, we have tried sawdust in different particle sizes, fine and or chopped woods, basically, different types, adding some other materials. The blending mixing protocol, okay, you have to add the culture of the mushroom to the feedstock. How do you do that? Okay, what process do you follow? I have some pictures to show that. Once this is, the feedstock is mixed with the culture, then it's the process of growing. Okay, we call it incubation. How to grow the mushroom. Okay, in the incubation process, the temperature. You guys have, some of you may have grown mushrooms. Temperature is one thing, right? It does not grow in the winter time if you don't have a greenhouse, or if you heat it up. Low temperature is not going to grow. Moisture is very important. Okay, the packing, the density, all the stuff, the ventilation, is all important factors. Here's a cartoon. I Dr. Philip. I have to get his name right. Okay, Philip Mstislavsky. Very long name. I tried a few times to get it right here. He pictured this thing. I think it's very, very nice. Okay, here this cartoon kind of depicts two mixing protocols. In the first one, see, you have the feedstock, sawdust, for example. This is the culture of the mushroom. You mix them together, you mold it, you put it in a mold, and then you put it into an incubator, and for some time of growth, and then you move it to a dryer. Here's your sample, your product. Or you mix the culture with the feedstock. You first let the mycelium to colonize, to grow first, for some time, for a few days. And then you would mash it, chop it, and then you mold it, and then put it into the incubator. We found out that's, first of all, can fasten the process, can accelerate the growing process, and it also allows, the matrix to be more sturdy. Put it in the plain English here. Okay, more extensive growth of the matrix to bind all those stuff together. So just the two examples of what the blending mixing protocols, what difference it can make. Here's a picture of some samples in an incubator. And if you zoom in, look at the material, okay? To answer Tom's question here, you still see some raw material. It's not 100% digested, but all those gaps, they are filled with the matrix, with the mycelium. So the air is fixed inside those voids or in the tubes, so that there's no convection going on if it's heated up. So that's how we make it very insulative. Okay, how the values of the R values is very high. We were playing with the different protocols, to mix them together. Different blending, different ingredients, different packing density, and even the incubation time. Okay, so just a table to summarize, the work we have done, kind of in the background, to optimize the process so that we have selected those that is very efficient in producing, in growing those insulation materials with consistent properties. Okay, lots of work, lab work being done by our research assistants. I forgot to mention the names. Maria White was one of them. Kellen Lee is one of our graduate students who have been helping with the projects. Some samples we produced in the first phase of study for mechanical testing, they look very consistent. At the early stages, we have run some tests, like where you test those concrete blocks, for example, just unconfined compression test. Okay, and you would obtain those so-called stress, strain, how much deformation, see how it works here. Those are different recipes, okay, 5, 6 groups, and looks like this guy is standing out. And that happened to be our group number 3 over here, the standing out. Not just the compressive strains, but also the modulus, shear modulus. And here's the thermal conductivity. They're about the same density. This is about the same as the others, but overall, that recipe number 3 seems very promising. So we build on that and then make some changes, trying to improve the process. So let me not to go into the details here. Talk about mushrooms. There are many edible mushrooms, but also there are many toxic mushrooms. So always a question people ask, is this going to be toxic to my pet? If they chewed up, if I handle that, am I going to get toxic, poisonized? So we did do a toxicology test. It's very safe. As a matter of fact, if you take the sample out from the incubator, it's just like mushrooms. It's very fresh smelling. Okay, I mean, if you're too hungry, you could eat it. And some more mechanical testing here. Here are some small beam specimens, like the structure members. That you can see that we have some features. This is one of the newer specimens. Some scaffolding already built in there to accelerate this growing process. So it's not only growing from the outside, but also growing from the inside. So that can cut the growth time, the growing time almost to half or 1/3. Okay, something. It's made of organic material. Yeah. So fungus can actually digest some of the material and then integrate together with the scaffold. So that's something kind of interesting we found out we've used for. We ran 3-point bending test. If you're a civil engineer, you probably have heard about that, for testing the mechanical properties, very commonly used test. Here's a sketch showing how the test is done. You have 2 supports, you have 2 loading points, and you measure in the process, you measure the loads, the force, and the deflection, at the center point. So by this test, you can figure out the flexural rigidity. Okay, if you lift it up, it's going to break down. When you lift a piece of the supports, how stiff the material is elastically. You compress it, it's going to deform too much. If you embed it in the embankments or roads beneath the roads, it's going to deform too much. That's the modulus of elasticity. Thermal conductivity, of course, we talk about insulation, this is very important here. We use a very portable equipment called the thermal analyzer that is capable of measuring the R value. It's actually, we call it thermal conductivity. That's the inverse, that's inversely proportional to the R value. The lower the conductivity, the higher the R value, okay? The specific heat, okay, or the diffusivity. All those numbers. This is a 2-needle equipment, device. We plug it in there, and then you start the testing process. The idea here, is to have 1 needle to heat up. Okay, you measure how the temperature raises, time and temperature, and then you shut down the heating source. You measure how fast the temperature drops, because inside the specimen, the only mechanism for heat conduction or heat transfer is conduction. So it's conductivity. Okay, so this equipment is it's a very portable, is low cost. Compared with some other tests, this is very simple. This piece of equipment is still expensive, about $6,000, for a small this size. Okay, but it's very useful. The accuracy is about 5%. We are pretty happy with the accuracy. So a couple of equations. This is for heating. This is for cooling, and those parameters. Actually, B1 is directly, or inversely related to K. K is the thermal conductivity. Just one example how we figure out the thermal conductivity. Not too much in the theory here. I'm going to show you some numbers here. Okay, you're all engineers. Comparison, for example, of the density. This is the dry density. Okay, those are our latest, 5 recipes. Okay, this is the latest results, very fresh, a couple of weeks ago. This is the competition in the market, EcoVative, for packaging purpose. Okay, so it's about the same, I would say. The blue boards that you buy from Home Depot is still lighter I would say, okay, we still have some ways to go, but we have some ideas to improve that. The thermal conductivity here, okay, our numbers is about the same as the blue boards. So very encouraging, very promising here. If you talk about insulation, it's about similar performance. Now, compared with the market, similar type of material, 50% better, or the R values is twice as large. Okay, if you use our material to make a box to ship your fish to your friends, it can last twice as long than the innovative material. Okay, or about the same time as if you use those EPS foam boards. Okay, so we're very happy with the results. We're excited about that. How about the mechanical strengths? If you handle that, it's going to break apart. This is a comparison here. This is the blue boards. This is our numbers here. Recipe number 1 stands out beautifully. Okay, it's about there. Okay, much better than the innovative market competition that we're very happy with. The modulus, how compressible it is, how much deformation it is going to have if you have a load on that. So our numbers, this is for this one is the higher the better, of course. For the market value, for the market competition, always all of our recipes are better, by a factor, of 1 or 2, even 3. So that is very encouraging. For the blue boards, there are different grades, different recipes there. It's right there. Okay, it's comparable. I put it this way here. I did not have numbers here. It's a range actually from here to here. So our numbers fall in between. And talk about production here. Last summer we tried to produce a few larger pieces. People wanted to try that. Okay, it's not for sale. Okay, it's just for experimenting. So we produced 3 4x8 feet pieces. They're about 2 inches thick, and turns out to be pretty good. That those 3 pieces are now being tested at the Cold Climate Housing Research Center, side by side with the blue boards and some other materials. 2 goals or 2 parameters we want to check. One is the air quality, of course, inside the panel. Okay, lots of research was saying the petroleum-based product would have toxic emissions in the air. Not much, but there's some. Okay, so we're going to check, how the air quality compares with different panels, different materials, and then moisture infiltration, all those other aspects. So it's being tested now. By this summer, would have some results coming out. So to production procedure, yes.
Talking about moisture infiltration, is there an estimate comparison? What kind of vapor barrier this would be as opposed to?
We don't have yet, but I'm going to touch that one. That's a good question. I'll talk about, the question was about the moisture infiltration. That's one of the challenges we're trying to work on, but I'm going to get back to the question, okay? When we present this and people, are interested, they want to use that, natural question was, how do you produce that? What it takes to do the production or mass production here. I think it's quite doable, from first cut, envision, I would say, you would have a few silos to store those raw materials, either forest waste material or agriculture waste, you would store them, with some other ingredients there. And then it's going to be proportioned, to a conveyor belt, moving, to I would say, here's mixing them together, and then you have to sterilize them, because for those natural materials, you have lots of microbes there. You don't want that thing to be competing with your mushroom, okay? So sterilizing definitely is one process, maybe number 6 here. And then once it's sterilized, you have to mix those material with the culture of the mushroom, okay? You could have different ways of doing that. And then once it's mixed with the culture, we call it inoculation. And then you would move them to the incubator, where the temperature, the moisture is controlled, where you need some space there, of course, racks, for a certain amount of time, and then you move to a dryer to dry it up, to get rid of moisture, kill the mushroom. You don't want it to be mushroom to be live because it can keep growing if when they're used. And the process can be, there's no, I don't think there's any difficult part. It's just ramp it up. We need some initial investment to set it up. I don't think it's so difficult to do. Okay, but again, of course, there'll be, one key portion was how do you mix them together, and the scaffolding idea I mentioned a little bit, how do you mesh together with this thing? It's going to be happening probably in this stage, okay, or maybe even starting from here. You already have your scaffolding set up, and then this material is just being mixed, is already in place. Okay, so those are the things we are still kind of thinking, but they are, scaffolding idea. The idea is to grow, not just grow the material, but we want to have some structural control, okay, or control of the structural properties. So we want to grow this material in a controlled manner, and also provide some, scaffolding inside the material so that we can design the material properties, beforehand. Even we can predict, the properties, knowing that how much is going to be digested and how much is going to be left, and also those materials itself, they are organic. Okay, they can be made of those, nutrients that mycelium eventually is going to be able to digest some of that and integrate together with this thing. So it's integrated together. And it's not going to be like, parts by parts added together here, okay? So there's an integration process. So for this material, to summarize, it's rapidly renewable, okay? Yes, this question here.
Question. I'm not sure I understand. You said that these mushrooms in there, they eat some of the substrate. So isn't insulation supposed to last for a long time? Like you put it in the road or in your house, or your walls or something. I mean, you don't want it breaking down so that after 10 years it doesn't have the R value or whatever. So how are you addressing that if mushrooms are...
Good question. Yeah. The question was, if the mushrooms are eating up the substrates, how do you ensure that the material is going to last for a long time? It's not going to be eaten up when it's used. Okay. So back to these slides here. In the growing process, the mushroom, they are encouraged. Actually, we want them to digest some of the substrate material. Okay. But when we have enough mycelium, grown, at some point, we have to say, okay, let's make a cut, and then we would put this material in a high temperature oven to kill the live mushroom or the mycelium to stop the growing process, so it's dead. So it's basically neutralized. It's dry. It's gonna stay there. Yeah, so it's the process here. I think I have something in the previous slides. Do I? Yeah, it's the dry. There was that's okay. There was a dryer for certain temperatures, which is fairly much higher than the growing temperature. Yeah, so that's yeah.
All right, but there is no fruiting portion in this matrix, it's only the root portion, so there's no spores.
The question was, for this species of mushroom, the fruiting body, is how big is the fruiting body, right? Is the spores produced? There's no, fruiting body is tiny, small. We would inhibit that so that, it's basically the mycelium itself was live. Okay, there was no spores even. Yeah, and the mushroom was not able to produce any spores. We discourage that or inhibit that. Okay, so it's not producing seeds for more mushrooms. It's not. Yeah. There was one question about the what was the question again? Did you ask the question? The vapor barrier. Yes, the moisture. Yes. Let me see if I can find a good example here. It's probably back here. Okay. Okay, back here. Let me find that. Okay, I have a nice picture to show that. So the mycelium material itself, okay, when it's yeah, this one. When it's growing, okay, when it's hitting some different object, for example, here is all the organics, right? When it's hitting a mold which is made of glass or steel, then it's found out, this is like its enemy. It's something that's very different. I cannot digest. What it does is can do produce a special type of protein enzyme to form a skin to protect itself, just like our skin. Here is protect germs, bacteria to infiltrate to attack our body. So naturally, when in the growing process, there's a skin formed, which repels water very nicely. And we are also researching different measures to add redundancy. This is one defense. We don't want to rely on one defense. As an engineer, you always want some redundancy. So we are looking into some other sprayable, like latex, stuff to help to produce maybe another line of defense for the infiltration. But the material itself, because those are hollow tubes, so they are actually, resisting moisture pretty nicely itself already. It's very light material. It's not attracting moisture itself. Okay. So that's all actually one of the questions, that we are trying to address here. But to summarize, this material, that it's very light, and of course it's renewable here. That is the main point here. Okay, non-toxic, lightweight. The R value is about the same as the blue boards you can buy from Home Depot. That's as good as you can get. The thermal conductivity was like 0.04, very close to that of the air. Most important thing that this thing, when you don't want it, okay, it's biodegradable. Few weeks, depends on the temperature and moisture. You dump it into your garden, okay, it's going to turn into fertilizer. So that's, it's going to disappear into the natural environment. So that's the beautiful thing about this material itself. When decommissioned, it's biodegradable in a short period of time, compared with the polystyrofoam. It's hundreds, if not thousands of years. Okay, so that's the big difference over there. We do have a patent pending, with the U.S. Patent and Trademark Office, and potential applications. We do say, immediate application would be fish shipping boxes. People want to buy it. They like the idea of having some organic, green material to ship the fish, organic fish from Alaska, right, to their friends, and then you just dump the box in the backyard. So there's some applications there. The computers, for example, we buy. The iPads. You have those foam boards. It's just a kind of creating a hassle for the environment. So infrastructure, the insulation in the foundation, in the roads, parking lots, for the building insulation purpose, fill material sometimes be used. So I think we have some applications there. Yes.
All right, if you're using it as like a subgrade insulation, how do you prevent the degradation until?
Yeah. The question was, do you intend to use it for subgrade application? How do you make sure it's going to last for a long time here? Again, that backs to the question about the moisture resistance here. So the skin itself, is this first line of defense. If somehow in the construction process you damage it, we want to have some other preventions. For example, you spray some, water resistant layers on top of that, or maybe you add some, other measures to do that. But that's still something, we are, we're not trying to solve the problem overnight. Okay, that's application question. It's something that we have to, solve, down the road. Yeah. So the immediate application is probably not in, in the soil, not in a moisture environment, but in a more controlled environment. And later on, once we solve those problems, not just the water problem, but also fire problem, freeze thaw problem that we encounter in the cold environment. And of course, mass production, is something, eventually we have to solve if we want to produce. So with that, I want to thank, all those sponsors who have been generously supporting this idea, this project. When you have an idea, you need support, you need financial support, you need to hire students to experiment. Lots of dirty work, behind the front, to see if it's going to work. U.S. Innovative Fund and the ConocoPhillips Arctic Science and their engineering endowment have been generously supporting this project. We have many individuals, who have been a big support behind, encouraging us to, encouragement sometimes, makes a lot, means a lot to the team here. So that is our plan here. We have some time here, for more questions, I guess. Tom.
So the existing natural product is your competition.
Uh-huh.
Do you know how that is made, and do you know what kind of market share they have? You think how do you see your product compared to?
Yeah, good question. There was a question about the competition. That's EcoVadif. How big a market share do they have, or how our product is different from theirs? So that's also a very new company, startup company by a few folks from Cornell. Okay, that's one of I think that's the only one in the market. This is still very, very new. You see articles in Nature, in the issues talking about this type of material. I mean, science aspect for the mycelium material. So this is cutting edge research. For the EcoVadif, they have, they started a few years ago. They have been producing packaging materials, I think, for Dell. There have been, Dell is going to use some of them, to package for computer packaging here. I think since the advantage or the unique aspects of our product is, we use different mycelium, different fungus. This is a cold weather fungus, so it could, if needed, okay, grow in a cold environment, okay, in situ. That's one possibility. And we do have some. I think if you look at the properties here, the scaffolding idea that we invented, that we are experimenting, is producing some fairly good or superior properties. For example, insulation properties is twice as high. I mean, the R value is twice as high. So we have some methods that can produce better insulation properties, and also we can control the densities, better, because when you talk about shipping fish, 1 pound, if you have a 5 pound shipping box, that's not going to work. The shipping box has to be very light. I think in the density part, in the structural part, I think we have some edge there. So those are that's the only one competition we have so far in the whole world. So we wish to push this forward faster than it is now. We have some difficulties here getting a license agreement or getting the agreement signed between the startup. We have a startup company there, but we want to sign agreements with UAA. There's some negotiations to be done. We're still in the process. So hopefully that can be signed pretty soon. Then we can pursue grants like SBIR or some investment to push this forward. There are people who want to buy shipping box from us. We don't have it yet. I mean, this material is already ready. We just need to produce them, and producing is not difficult in a small scale. You can see, yeah.
What do you think the costs are going to be?
The cost of the product? The cost of the product, that's a good question here. We have not calculated it yet, but if you look at the ingredients, okay, they're not expensive. We're talking about sawdust, chopped, wood pieces or agricultural waste. It's probably just shipping cost. The culture, needs some time to to produce, but it's in the we can do it in the lab. You don't need a whole lot of culture to do that. The major cost, I would say, is probably going to be the investment for the facility to set it up, to make it work. That would be the major cost. The material itself is not costing much at all.
Back to building, how long does it take to grow it?
It's about a week. How long it's going to take, the question is, how long it's going to take to grow this material, okay? At the beginning, it took us about 2 weeks to grow a batch. Now we have cut down to about 7 days.
And this is in the incubator?
It's the whole process, yeah. Incubator, yeah, it's majority time is the incubator. That's the time consuming, that's the controlling point. Exactly. Everything else could be done piloted, but the incubator, it has to sit there for this long of time. So about 7 days, about a week, that is, I think with this probably potential to cut it down, even further when we tweak the processes, temperature, moisture, and the process. Yeah, so there's potential there.
And temperatures are kind of reasonable out of there.
Oh yeah, the temperature. The question was about the temperature. It's very reasonable. It's not like super high temperature. Yeah, just in ideal temperature and moisture, of course. Yeah, you just have to control that. Since our patent is still pending, so I don't want to talk too much about the numbers there. But yeah, that's kind of the part of the trade secret there. Yeah, there's a sequence there. Yeah, not very high at all. Is there any degradation due to UV exposure to UV? The natural lights. We have not done that experiments. Those are mushroom materials. You have it in the environment. The mushrooms. This is the kingdom. Okay, they are very tough. You have a wildfire, right? First thing growing after wildfire is mushrooms. They don't die just because of the harsh environment. They survive. Okay, so I cannot answer for sure. How, but if you do have that environment, that needs to be tested. I think if it's high UV exposure, but for many of the applications, it's probably more like indoor. Shipping box, so that would not be a concern. But yeah, another feature about this property here, it has a very nice sound absorbing property. It's just like sound, noise absorbing properties. Just very nice. So that could be a potential application too. For acoustic purpose. So this, it's a new material. We're still exploring, for the different type of applications. I think there's potential there. It's just a fun project to to work on. It's a hands-on and it has some amazing properties that sometimes even surprises us. At one point, we talk about the water absorption. We're dumping it into the water, right? Because it's so light, it's basically floating up. It's only 15% of the density of water. By the way it is now, so it's very light. It could be lighter in future. If you have a skin there, if there's no damage to the skin, water would have a hard time to get in there. Other questions?
We're using a subgrade application low or something. We're not going to kill it and kill mushroom alive. Is there a potential there to let it keep on increasing in size? Would it increase if it was buried, or would it like try something that moisture?
That's a good point. The question was if you keep the mushroom, live when you embed it in the ground, is the potential for this to grow, right? Or I think the other question would be, is there going to be easier for the material to last longer? If it's live, it's not going to degrade. It's going to keep growing when you have the right stuff there. So that has to do with the, maybe I can offer some, insight. If we elongate the incubation time, from 1 week, for example, to 4 weeks, we do see the additional growth of the mycelium. So, the substrate is going to be consumed, more substrate is going to be consumed. But for the mycelium to grow, you need oxygen. Hold on. Was carbon dioxide maybe? You need ventilation. Let's put it this way. Okay, that's another aspect. It's actually absorbing carbon dioxide in the process. Okay, so, but if it's not ventilated, then the growth will be slow, very slow. Yeah, so I think it's going to be like dropping exponentially, because when there's no air, there's no, you are basically shutting down the process. But the mycelium itself is going to be almost like stay hibernating, there. So that's another possibility. We could keep it alive in the ground. It's not going to rot. It's not going to decompose. But then the insulation property, is going to be degraded. It's going to be compromised. Yeah, because you have moisture there, right? So unless you get rid of the moisture without drying it up, then you still have the air. You don't have the ventilation, so it's not going to grow. That's something we were also experimenting, talking about that, the life thing. This mycelium is amazing. There's another amazing property here. Okay, if you put two pieces of the material together, if it's live, they're going to glue together naturally. So that's something we were also trying to take advantage of. How do you stitch together two pieces? If it's alive, they're going to glue together, because they're trying to find whatever nutrients is there, right? If they're the same species, they're going to mingle together, just like us having a party, So yeah, that's reminding me about that. Yeah, we were thinking about those other possibilities, keeping it alive. Yeah.
It kind of prefers a CO2 rich environment during its incubation period.
We had, the question was, do you prefer a environment which is rich in carbon dioxide? We have not controlled the carbon dioxide, but from the basic knowledge, when the mushroom has to grow, they are actually absorbing carbon dioxide. So maybe in future we could, by providing more carbon dioxide, we can accelerate the growing process. That's something we have not experimented. Yeah, it's yeah, maybe we can set up the plant by a power plant, and then take the exhaust, right, to help to fix some of the carbon. That's one of the problems Tom is facing, right? Global warming or global change. We have too much greenhouse gas emitted to the environment. Yeah, we could exactly. Yeah, we definitely could use the waste. It's about room temperature. So that's the growing environment we are using. It's about we don't have to heat up too much. See, so yeah, that's definitely something. So it has the potential, to help to get rid of some of the waste that we don't want, and then turn them into something useful. I think that's probably the significance of this research. Producing an alternative material for our infrastructure construction, and also help to diversify the economy if we can set up a plant, here. We have lots of waste, trees, they're going to die, right? Yeah, forestry product, southeast, we have some of them there. Yeah, true. Yeah, supplying, of the ingredients is something there, but in the lower 48, there are plenty of the stuff people want to dump. I learned back, in China, they burn all those agricultural waste. That's one reason why the air quality is so bad. There's no better way to dispose those huge amount of agricultural waste. Yeah, so this could be one approach, one thing that we could help. Other questions?
Great job, Joey.
Thank you. Thank you.
Can you announce the Fungus.
Oh, the password for today's PDH is fungus. G-U-S. I'm sorry. Fungus. Fungus. Perfect. Thank you, guys.